So in the last video, we talked about the fundamentals of digital sound and of each of those samples and the considerations we had in terms of sampling rate, bit width, number of channels we use to represent sound digitally. In this video, I want to delve into the question of sampling rate in much more detail and ask the simple question of how do we determine what the appropriate sampling rate is. So we'll explain a little bit more formally what a sampling rate is, and we'll look at the Nyquist theorem, which gives us some guidance on picking a sampling rate. And finally, we'll also talk about fold-over, which is something that can happen that you usually don't want to happen if you pick a bad sampling rate that's too low for a particular project. So sampling rate is very simply put, it's the number of samples per second of digital audio. If you recall, we have this kind of very zoomed-in sine wave here. Each of these dots is a sample. It's simply asking, well, how many of these dots are we capturing every second? And because this is in terms of a samples per second kind of metric, we actually use hertz to represent it, the same thing we would use to represent frequency. For instance, 8,000 hertz is our sampling rate would simply mean that we're capturing 8,000 of these samples every second. That's how we talk about sampling rate. And now, how do we decide what our sampling rate should be? It's actually fairly simple. We use something called the Nyquist theorem, which is also sometimes known as the sampling theorem. And what the Nyquist theorem says is that the sampling rate must be at least twice the highest frequency that you wish to represent. This makes a lot of intuitive sense if you think about it. The reason for that is, let's think about our sine wave again here. If I have a sine wave going at, say 440 hertz, then I have 440 peaks and I have 440 troughs happening every second. So the minimum that I need to capture digitally in terms of those dots, those amplitude readings, would be for each cycle of my sine wave, I need to make sure that I have at least one sample to represent somewhere on my peak, somewhere above the zero crossing, and then something somewhere below the peak to represent below the zero crossing, somewhere down by my trough. So I need 440 peaks and 440 troughs, or 440 above zeros and 440 below zeros, to be able to capture these 440 cycles of my sine wave in a second. So I simply would multiply 440 by 2, and I'd end up with 880 is the sampling rate that I would need. So in reality, we're not looking at every individual sine wave or frequency component that we want to represent. We want to come up with some general sampling rate that's going to work really well for a lot of things. So what should that sampling rate be? Well, we can kind of deduce this logically. We've talked about the range of human hearing is going from roughly 20 hertz up to 20,000 hertz. So if we take 20,000 hertz, and we multiply it by 2, this is some pretty easy math here, we end up with 40,000 hertz. So we know that the sampling rate must be greater than 40,000 hertz. And so the number that we usually end up seeing is 44,100 hertz. The reason for this has to do with the history of the early days of digital recording and some decisions that Sony and other manufacturers made in the late 1970s that aren't really worth getting into here. But that number has largely stuck. That's what we use on compact discs in particular, is 44,100 hertz as our sampling rate. You'll sometimes see other sampling rates. You'll see like 48,000 hertz, for instance. You'll sometimes see higher rates like 96,000 hertz or even 192,000 hertz in some very high fidelity recordings. And the reason for that, of course, is that if we have this sine wave here, sure, it's nice to be able to capture at least one sample somewhere on the peak and one somewhere on the trough, but that's not going to be enough to really capture the entire shape of that sine wave, the entire curve. If you want to get a really, really nice representation of it, you're going to want as many samples as possible all along the way. So the higher our sampling rate is, the better resolution we'll get, and the better we'll be able to represent those curves. So I want to talk briefly here about what happens if our sampling rate is too low. we get something called fold over. So if our sampling rate is too low, it's not just that the other, the frequencies above the Nyquist frequency, which is that highest frequency we can represent. It's not just that those frequencies disappear from our sound, but they actually they turn into other frequencies in the sampling rate. So I want to show you what I mean here. Here we've got a sine wave here on this top image here. And we can look at the number of cycles here from peak to peak, peak to peak, peak to peak, and peak to peak. So there's 4 plus a little bit more in this image. And this is a sampling rate of 44,100 hertz. Now if we take that same sine wave and we reduce it down to something crazy low, like 284 hertz, we end up with something like what you see in the bottom. So here, we're still getting a periodic sound here. It's not a sine wave anymore because we've lost kind of the resolution of that curve. And it's also not the same number of cycles anymore, but we are getting cycles. We're getting 1 full cycle plus a little bit more in this particular square of time. And so we're going to hear that as a periodic sound. It's going to have a frequency to it, but it's not going to be the original frequency that we expected of that 440 hertz sine wave that we had in the top image. So now I want to look at these sampling rates in practice inside of Reaper. And so what I have in this demo here is I have just a simple 440 hertz sine wave loaded on my track here. And I have a special plugin here which lets me change the sampling rate of the sound dynamically, so we can hear what happens with that sine wave at different sampling rates. Right now it's set at 44,100 hertz. And then over here we have a spectrum analyzer, so I can see what frequencies are actually present in the sound. So at 44,100 hertz, I have my 1 sine wave peak here right at 440 hertz, the way I would expect. As I start lowering that sampling rate, at first it doesn't matter because I'm still following the Nyquist theorem. But as it gets lower and lower and lower, we start to see the folding over happening, and we start to hear it as well. As those folded over frequencies start coming in to my sound. I'll go back to 44,100 hertz. So you can hear a similar phenomenon if instead of just listening to a sine wave, we look at a real sound like a drum loop, something like this. So again, that's at 44,100 hertz. So that's a good sampling rate for the sound. But as I bring this down, we'll start to hear a lot of frequency content getting lost. First, it'll sound like we're just losing some of the higher frequencies, so it sounds a little bit darker. And then as it gets lower and lower, we'll start hearing more of that fold over and actually hear other pitches start coming in. So you can get a sense both of the frequency content that's lost as I lower the sample rate, and also of the frequency content that's folding over as I lower that sample rate. The final example I wanted to show you was to go back to that chirp sound, that one that sweeps gradually from 20 hertz all the way up to 20,000 hertz. And so this is a really clear demo of this practice of fold over. So again, if I'm at 44,100 hertz, I'll just hear that original chirp the same way we've heard it before. And we can see this on the sonogram here as it's going up and up and up steadily in pitch. But as I lower that sampling rate, we'll start to hear and see it folding over at a certain point. So you can see the fold over as it's going down much lower than it was before. And the more I lower this, the lower that fold over is going to start happening. So we're not getting the chirp from 20 to 20,000 hertz anymore. It's getting kind of stuck when it hits that Nyquist frequency and coming back down, going up and down as it's folding over. So just to quickly review here, in this module we talked about the Nyquist theorem as a way to figure out an appropriate sampling rate, that our sampling rate needs to be at least double the highest frequency we want to represent. And we talked about how we kind of arrived at 44,100 hertz as a fairly standard sampling rate. And we talked about the fold over and other effects that can happen when we're recording at a sampling rate that's too low. In the next video, we're going to get into the question of bit width and how we decide what resolution we need to represent the amplitude of each sample.